Welcome everybody to today's Relativity Ask the Expert webinar. Today's topic is random samples and common statistics, an introduction to the use of statistical sampling in relativity. And I have to say I am very excited to do today's session. Who is this person that's excited to do a session like this? Well, my name is Jeff Gillis. I'm a member of the solutions team here at Relativity. My specialty at Relativity is analytics, but my first love is math, and my passion is things mathematical and things about statistics and random sampling. And so I've been looking forward to doing this session for quite a while, and I think we'll have a great time. Just a note, you get RCE credits if you're watching us live. If you're watching the recording, you just get the pleasure of the content. Before we get into it, please let me know if you cannot hear me or if you cannot see my screen. My guess is that people generally can. I'm getting a lot of yeses, so I think we're in the clear here. Okay. So our agenda for this session today, I'm going to start with kind of a high-level introduction to sampling. Then I'm going to get into a little more detail, talk about margin of error and confidence level, so some of the math behind it. We'll talk about sampling within relativity, and we will talk about, we'll get into a demo and show you how to do a sample in relativity. We will then pivot and talk a bit about precision and recall and F1 and elusion. And at the end, we'll wrap up and take any questions. I do have the question box here. If you do have questions as we go along, you can type them in. By and large, I'm going to answer them at the end, but if there's something that needs clarifying, or if, God forbid, my audio goes down or something, please don't hesitate to let me know that. Usually when someone has a problem with my audio, it tends to be on their side, but yeah, you can use the question box for that. So let's get into the content. So introduction to sampling. Anytime you do a session like this, you start, your mind gets in the mode of noticing things, and so you start noticing the topic in the world all around you. So sampling is really all around us. Something that's not quite on target for what we're talking about today, but certainly this time of year, we always like to have a nice big scoop of ice cream. We get charged a nice big $7 for a huge waffle cone with like 3 scoops in it. So you want to take a little sample of those flavors before you commit to that big purchase. Would you go to the doctor? They take a blood sample. Thankfully, they don't take all of your blood, because that would be very painful and probably fatal. They just take a little bit of your blood, and then they test even a little bit of that little bit. But from that sample, they can determine how your overall system is doing. When you think about wildlife, biologists and botanists, they want to understand what's happening in the natural environment. So they go out and they sample fish, or they sample plants, and from those samples they project truths about the overall ecosystem as a whole. They don't have to tag every single fish to do that. They can get a sample of them, then they can do some complex math to try to figure out how those samples project onto the greater population. I was recently reading about the snow leopards in the Himalayas, and there's so little known about them, so they're putting these cameras out there to catch them, but it's like there's a lot of extrapolation you have to do to try to interpret what the samples are telling you about the real world. Random sampling, which is what we're going to focus on today, and in relativity, it's much easier to use sampling than it is if you're trying to learn about the snow leopards in the Himalayas. With random sampling, it typically is used when you wonder about a frequency. So how common is something? How frequent is something? What is the rate of something? So political polling, what is the rate of support of this candidate? Or in manufacturing, what is the defect rate of the widgets coming off the assembly line? When we have, in eDiscover, we might have what percentage of documents in our collection are in a particular language, or what is the error rate of the reviewers making coding decisions, or the machines making coding decisions. So these are all cases where we're interested in the rate of occurrence. More broadly, I think there's a few things that I look for when I ask myself, is this a good problem to use random sampling to solve? So the first one is there's a cost associated with measuring every single item, and the cost of measuring a subset is much less. So like finding all the documents in my collection which are Word documents is probably not that hard because there's probably a field that I have in Relativity that tells me what a Word document is. So I can do the whole collection. But if it's something much more expensive, like that was going to require me to read documents, then that cost is high. Now this cost can be monetary, it can be processing time, it can be the opportunity cost of me doing this instead of doing something else. So there's a variety of ways that you can measure cost, but is it costly to do it on everything versus doing it on a small subset? The second question I ask is there a short shelf life? Apologies for the picture of the moldy strawberry. I saw some pictures that were much moldier, so this one was fairly tame, but you know, the shelf life, is this perishable information? Knowing this information today versus tomorrow versus next week is going to be dramatically different. So if I've got a manufacturing assembly line and I'm producing defective widgets, I need to know that now before I produce another million of them. If I've got a reviewer that's coding incorrectly, I want to QC my reviewers early on to make sure that things are going well before I pay them for 6 weeks of work and then at the end realize that they've been doing things wrong. So that shelf life can be short, and you'd much rather have an okay answer now or a good answer now than a fantastic answer 6 months from now when the information is no longer valuable. And then the third characteristic is the one I mentioned on the previous slide. We're not looking for all items with a characteristic, and maybe eventually we'll look for all items, but it's valuable now to know how many items are out there. So it's that how many question, not every single one. So those are the things that tend to get me excited about using random samples. So what is the benefit of using random samples? Well, kind of derived from that. We know answers more quickly. We don't have to invest as much time or money or opportunity costs in getting those answers. And not only that, these are approximate answers, but they're approximate in ways that we can project onto the whole population. So we know what the actual rate or range of the actual rate would be based on what we see in our sample. So it really boils down to time is money, which is apparently Benjamin Franklin, at least according to the internet. He's the one that coined this phrase, but you know, you can adjust your strategy if you know something sooner. You can redo the work when it's fresh in everyone's mind. So if you correct a bad reviewer or a misguided reviewer quickly, then they remember those documents that they coded wrong and they can get back in there. Or if you've just processed a bunch of stuff and you realize you've got problems, you can go fix that right now while it's fresh on your mind. And you have confidence to proceed to the next phase. You can say, let's move forward with this project. Let's move forward with the next step because I don't think we're going to have to back it up because we've got some benefit of the random sampling there. Okay, so let's talk about relativity in particular. When do we like to use random samples in relativity? You know, the one thing is you have to have sufficiently many objects. If you have 10 objects and you random sample them, you're not going to get too much benefit. But so where do we have a lot of objects? Certainly documents. We have lots of documents in our system, sometimes many, many millions or tens of millions. So we might want to QC those documents. We might want to QC the systems like the OCR or the processing or the production images. So there are software systems, they do some work, and we want to see if those systems are working as expected. There also might be people involved. So humans are coding documents, humans are redacting documents. We want to QC those coding decisions or those redactions. We also, you know, we often do a richness estimate with a random sample. So this just tells me what percentage of my documents are responsive, and that can be useful information to know for a number of reasons. And then there's all kinds of applications of sampling and things like clustering. I actually did a whole nother webinar on how to apply random samples to conceptual analytics. And with clustering, you know, sometimes you use clustering, conceptual clustering, to get a high-level view of your data, understand what topics are covered. If you cluster a 100,000 sample out of a 10 million document collection, you're going to be able to answer that question very strongly and really understand what's in your data. And it'll take less time to do, so you'll have it available more quickly, and you can react if you say, oh my gosh, I collected a bunch of stuff I didn't intend to collect. Let's pull that out of things now instead of finding that out 2 days into review. Now, other objects that you might sample in relativity, if you're having a bad day, you may have many, many processing errors, so you could sample them and dig into those. Other types of custom objects that you have a lot of that are otherwise difficult to measure, that you want to have some kind of eyes on, you could certainly do that. Repeated content filters is something that you sometimes have, 1,000 of, and if I'm gonna hand inspect 10 of those, I'd rather hand inspect 10 random ones than hand inspect the first 10, because the first 10 might have some bias in them that doesn't really reflect the whole population. Now, 10 is a really small sample, so that's maybe a tricky example, but I think randomness is a good tool to have in the forefront to your mind. So let's talk about margin of error a little bit and kind of try to characterize the error and how that occurs. So consider this situation. I've got 1 million documents in my workspace. I take a random sample of 1,535, okay? And I run language ID on that sample, and I find that 30% of these documents contain some Russian in them, according to language ID. So I can go to my boss and say, hey, my sample is 30% Russian. I could say that in Russian too. I could also say my workspace is about 30% Russian. It's 30%-ish Russian, okay? Well, what does 30%-ish mean? What I can really say, because of the size of my sample, I can calculate and say, our workspace contains between 27.5% and 32.5% Russian documents. In fact, I'm 95% confident that that statement is true. That's what random sampling does. It gives you those tangible numbers to apply. And if 95% sure isn't good enough, I can say, well, I'm 99% sure that it's between like 26 and 34. And I'm 99.99% sure that it's between like 25 and 35. So you can get more certainty with a slightly wider margin. But the key is this could be, and again, this is 95% certainty, this could be something that could be important to you. You might say, oh my gosh, we only have 1 reviewer out of 100 that speaks Russian. We need to staff some more Russian reviewers because we're going to have a lot of documents. Or maybe I'm worried that some of these are false positives due to email headers. Well, I could go and hand inspect those 1535. It's not easy, but it's not that hard. So I could maybe do some other things with that sample and get a different rate and do some more things like that. So this is really the idea of margin of error, is putting some math behind that kind of hand waviness of saying about 30%. It really allows you to be more specific. But oftentimes it's that even with that range, that gives us something we can act upon. Okay, so here's an example that you might see in the news sometimes. You pick up the newspaper and you see a political poll and it says candidate A has, we did a poll today, candidate A has 45% support, candidate B has 44% support. So you might, I certainly have heard news media say, well, A is leading, right? A is ahead by 1. Anytime you see something like that published, you should often see a margin of error. If you don't see a margin of error, you're really dealing with someone that's bending the math. But there's a margin of error applied to that. So I would argue that saying A is ahead by 1 is really not the right way to say it, because with that margin of error, what that means is like B could be 4% higher at 48, A could be 4% lower at 41, so B might be ahead by 7. It's not as likely that B is ahead by 7 as that A is ahead by 1, but it's certainly within the margin of error. It's within the realm of the 95% confidence. More likely, B is ahead by a little bit less because these things are kind of like bell curves that are lumped in the middle. But B being ahead by 3 is a lot different than A being ahead by 1, because that means that B would take office, not A. So it's critical which of those is the case. What this really means when we measure and see that A is ahead by 1 is that A is more likely to be leading, but really it's too close to call. If you did this poll again tomorrow, you might find B ahead by 1, and that doesn't mean that any voters change their minds. It could just be how random sampling works. Sometimes you're a little this way, sometimes you're a little that way. So really what you're dealing with here is an instance where the tool that you're using is not able to accurately give you the answer of what you're trying to measure. So if you're using a yardstick or you're using a meter stick, if you're in another part of the world, it's about the same size, but you can't measure the width of a human eyelash. That's like 1/10 of a millimeter wide. You can't measure that with a yardstick. No, it's not a matter of trying harder. It's not a matter of using a magnifying glass to look at it harder. It's just not the right tool to measure it. So sometimes the tool is not right, and what you should do is just come right out and say it. Say, look, our poll shows that this race is close. It's neck and neck. We really don't know who's leading. A is slightly more likely, but I wouldn't even say that. I would just say it's too close to call right now. So you need to interpret your margin of error in a reasonable way. One of the nice things about sampling, about margin of error, is this concept that even with large populations, you can use small samples. When they do political polls, they typically survey like 1,000 people, and then they project it onto what 100 million voters are going to do. And that's really just a characteristic of how the math works. So if you look here, I have a table, I ran these numbers, and it's like if you have 500 things you're sampling and you want to get a margin of error of 5%, you got to sample 217. If you have 100 million, you only need to sample 384. So whether you're sampling 100,000 or 100 million, it's really the same. Now, 5% of 100 million is 5 million. 5% of 100,000 is 5,000. So there's no free lunch. It's not exactly the same in that sense. But by and large, the percentages is what's interesting to us. For the most part, when we're looking for what is the general rate of something, that's good enough, because like the Russian reviewers thing, I don't need to know that I need to staff 28 or 29 Russian reviewers, but I know that I need more than one. So you can use these numbers to your advantage and then go and act upon them. Okay, confidence level. I mentioned this a couple times so far. So confidence level really goes hand in hand with margin of error. Any margin of error is based on a confidence level, and you can't kind of have you can't have margin of error without confidence. 95% is just like the de facto norm that the world uses for historical reasons. That means 19 times out of 20. And I know that people struggle with the idea of not being 100% certain. Certainly in e-discovery, certainly in the U.S. legal system, the certainty is not the measuring stick. The measuring stick is proportionality, it's reasonableness. So being 95% sure can be very reasonable. But think of it this way too. In real life, we're used to talking in certainty when we really don't have certainty. If I say, hey, tomorrow night I'm going to or Saturday night I'm going to the movies with the Jacksons, I'm not saying I'm probably going, I'm saying we're going, right? But the Jacksons have to get a babysitter, and their kid might get sick, or the babysitter might get sick, or the babysitter might flake out, right? There might be a storm, I don't know. You know, when we travel, we say, hey, let's grab a cab from the airport together to get into Relativity faster. We could take the subway too. But you know, flights aren't always on time. We talk like we're going to share a cab together, but my flight's delayed, your flight's delayed. It doesn't happen. Probably 10% of the time that's not going to work, but we still kind of talk in certainty. You tell your boss you're in sales, you tell your boss you're going to close a deal. Well, you know, things happen. Acme got acquired. Now we're not going to close the deal. So, you know, I would say between the legal system and just the fact that we tend to talk this way, I think sometimes you get a little bit weirded out by the idea of not 100% confident, but what I would say is nothing is certain, and 95%, 99%. If you operate a business only based on certainty, you're not gonna get very far in life. We have to make calculated risks in our life, and so confidence level is a way for us to say we took a sample, we did some due diligence, we are 95% sure. The other thing to point out about this is if it's in that 1 time out of 20 that it's wrong, it's not going to be wrong by much. It's a bell curve. It's off by a little bit. So 95% of the time you're within the margin of error. 5% of the time you're outside of it. The chances of being way outside of it are super, super slim. And you know, it's like the chances of winning the lottery. I apply to the Hamilton lottery every day, trying to win tickets to Hamilton. You know, I don't really think I'm going to win them on a given day. So So calculating margin of error and confidence, it's basically a matter of the sample size and it's a matter of the confidence, so that you get the margin of error with the sample size, the population size, and the confidence. And you can do this very easily in relativity. So relativity has, when you do a sample, we'll show this in a minute in a demo, you specify the confidence and the margin of error, and you get a sample size. And you can do it the other way. Well, in relativity, you give those two, and in other online tools, you can give it. You can do it by plugging in the other way, plugging in the sample size. There is a third parameter that can be used to calculate margin of error, and you'll see this in some of the online tools. By online tools, I mean Google calculate margin of error, and you get pages and pages and pages of people's tools, online things that you can use. But there's this prevalence rate that's involved. And when relativity does samples, it does what a lot of these tools do, which is to say, I'm going to be conservative. I'm going to assume that it's a 50-50 prevalence of what I'm looking for. And so it's going to give kind of the worst case margin of error. However, when you're measuring things that are either really rare or really common, like 90% prevalent or 10% prevalent, then your margin of error is actually better. It's tighter. It shrinks. So if you can assume those things about the prevalence, you can actually get a tighter margin of error. And I'm not a card-carrying statistician that's going to endorse your approach per se, but if you do some reading and you do some research, you'll find that this is the case and that you can use the prevalence parameter to tighten that up. So if you go online, there's a tool at a site called RowSoft. Again, this is not the views of relativity. This is my own personal view. I like this particular tool, but there's other ones out there that allow you a lot of granularity. So you can see here, you can plug in that response distribution, it's called, defaulted to 50%. It says leave it at 50 if you don't know. But you plug in your population size, your margin of error, your confidence, and it'll calculate your sample size, and you can play around with the different numbers. So that's just a little bit a word about calculating this. So let's jump into a bit of a demo. So I'm going to bring up relativity here, and you should see my workspace. So here I am. I'm in Relativity 1. I've got, you can see a widget at the top that shows the distribution of file types in my collection of 64,315 documents. Okay, and what you can see is that just over half of my documents are Outlook, about 20% are Microsoft Word 97, and about 15% are Microsoft Excel 97, and et cetera down below. So if I grab a random sample in relativity, I can see kind of how that sample is performing by looking at these graphs. So to do a sample in relativity, you can do it on any object as long as the permission on that object type is set to allow for sampling. And if you do that, you'll see this little icon up here that says sampling. I'm going to click on it. Now I can do fixed, where I type in how many documents I want in my sample. I can do percentage, so if I said 1%, it would give me, I guess, 643 documents is 1% of my thing. I don't really use percentage very much. I pretty much use fixed or statistical. If you do statistical, again, at an assumption of 50%, you're gonna plug in your confidence level, say 95, your margin of error, say plus or minus 5, and then I'm going to click sample. So this is the one that I had in that slide before. That was 384 for very large systems. You can see it's 382 for this collection. So now I have 382 documents, and lo and behold, about 50% of them are Outlook messages. A little under 20% are Word documents, so that dropped a bit. My Excel bumped up a bit. It was a little over 15%. But these are all within a reasonable margin, certainly within 5% of the original numbers. And what I could do is, then usually I would have these numbers first, and then I could project onto the population. So if I saw in my sample 50% Outlook, I'd say, yeah, I got between 45 and 55% Outlook message files on, essentially MSGs in my overall collection. Now, if you have a smaller sample, you're going to get generally a little bit more wide-ranging results. So let's do a sample of 20 documents. I'm going to sample 20 documents. Now what I see is 55% Outlook, 25% Word, so those are both up by about 5%. Excel's at 15%, okay? I'm going to sample this thing again. Let's do 20 again. And hopefully, the cardinal rule of doing demos is you should never do a demo of something where you don't know what the answer is going to be. I am totally breaking that cardinal rule right now. This is like I'm taking you to the casino, I'm letting it roll, and let's see if we get blackjack. So this time, aha, it's different. So I have 35% Outlook. That's way below my 50%. I've got 30% Word. I've got 20% Excel. I did this yesterday like 20 times, and I got different answers. I never got it below about 30% Outlook. I think I exceeded the margin of error once. I think the margin of error with a sample size of 20 is about 20%. Again, you could use a calculator for that, but you can do these types of things and you can see how this will waver. So that the larger your sample, the closer you'll get to the original numbers. The smaller your sample, the more likely you are to vary. Maybe you hit it right on the nose. That'll sometimes happen, but you can also get weird results, and that's just a function of sample size. Okay, so we will come back to relativity later, but let's jump back into some of the discussion here. Okay, so we're going to talk about precision and recall, which are terms that you've probably heard before, and we'll talk about elusion rate, which is one that you may not have heard, but is kind of in the same realm as that. So when we're talking about precision and recall, sometimes F1 comes up, sometimes elusion. What we're really talking about is measuring the accuracy of something. So it could be a test, it could be a model, it could be an algorithm or a prediction, but we're talking about measuring the accuracy of that. And so you can think of this in terms of medicine, because actually these terms they have very similar analogs in the medical world, in the scientific world of various types. So think of a medical test, right? You go in, your throat hurts, you go to the doctor, they give you a strep test. Now that test has a few different outcomes. It can say you have strep when you really have strep. That's correct. It can say you don't when you don't. That's correct. It could also say you have strep, but in fact you don't have strep. It could say you don't have strep, but you do have strep, right? So it can be wrong in two different ways, and the consequences of each of those types of being wrong can be very different. So what you're really after is either a balance. You want it to suit the needs of what you're trying to do. So let's think of a different condition. Think about rabies, okay? So rabies is a fatal condition that has a very easy treatment. So if you had a test for rabies and it would often say you didn't have rabies, but really you do, and then you don't get treated, that is a very bad thing, right? If it says you do have rabies, but really you don't, well, the shots aren't that bad. They don't give you shots in the stomach anymore. I learned that one recently. I didn't learn it firsthand, but I learned someone was talking about rabies shots, and apparently it's like a shot in the arm now. So yeah, it's inconvenient to get a shot in the arm. It's not fun. It's not what I do for fun, but it's better than the alternative. So that's a case where false positives and false negatives are very different. You can also have tests for very, very, very rare things. So suppose you had a condition which occurs in 1 out of 100,000 people, and suppose that I have a test that's 99.9% accurate, okay, on that condition. Would you buy my test? I'm selling it for $20 a pop. Would you buy it? Well, you need to know when it's accurate and when it's not accurate, okay? So my test could be for any patient that comes in, it says, nope, you don't have the condition. And for 99,999 patients out of 100,000, it is correct. But for that one patient who does have the condition, it's incorrect, and that's the only thing that you're buying the test for, is to see if someone has that condition, right? So it really matters what type of errors you have. You have to take this into consideration as you do this. Now, I'm not in the business of selling medical tests. I'm in the business of selling software that does e-discovery. So we often have these TAR algorithms. We're trying to measure the process. We want to know about false positives and negatives. And we want to know when it calls a document responsive and really it isn't. We want to know about when it calls a document not responsive and really it is. So in our world, we need to weigh those factors, and we need to decide which is more important to us, and we need to have tools which can allow us to measure each of those. Okay, so precision and recall are the two main tools that we've inherited from the overall IR information retrieval space. So precision says, when my algorithm says it's responsive, can I trust that decision? Okay. So it only looks at when the algorithm says it's responsive. It doesn't look at all at what happens on the predicted non-responsives. But to measure this, we look at all the documents predicted responsive, and we say what portion of those are in fact responsive. Okay. Recall asks, how completely did we find the responsives? How complete of a collection did we get here? Do we leave a lot of them behind, or do we really collect a lot of them? So the problem with recall is it doesn't on its surface penalize a shotgun approach. What I mean by that is my algorithm could say every document I see is responsive. the recall is perfect because every time a document really is responsive, the algorithm predicts it responsive. But it's also useless because it didn't do anything. It just brought forth everything. So precision has a similar kind of a thing. If it only predicted one document responsive, it might be correct, but if it left behind millions of documents, that's useless too. So these two things need to be taken with a grain of salt. That you have to consider which ones matter to you. But recall, the calculation is just we look at the actually responsive documents and we figure out what portion of them are predicted responsive. Of course, if we knew what the actually responsive documents were, we wouldn't even be in this business. So this one, recall, is a bit trickier to calculate because it's based on that. We'll talk about that some more in a bit. Okay, so this is too many words. Let's talk with pictures a little bit. So I've got some diagrams that kind of illustrate all this. So here's your document universe, okay? This is a very small workspace. It's only got about 30 documents in it, but imagine this was millions and millions of documents. So within that document universe, unbeknownst to us, but known to the future, to the people in the future, there are responsive and not responsive documents out there. The responsives are on the left-hand side of our screen, conveniently. The non-responsives are on the right. Also within that document universe, we've got an algorithm, and that algorithm shines a spotlight on the documents that it thinks are responsive. So the documents inside the circle are predicted responsive by the algorithm. The documents outside the circle are predicted not responsive by the algorithm. Okay? So what is precision? Precision is we look at the predicted responsives and we determine what portion of them were actually responsive. So our universe is what's inside that circle. You can see along the top of this diagram here, I've got it's this left half of the circle divided by the whole circle. That's how we calculate precision. So if we think of that in a table format, here we see 10 documents. They're all predicted responsive according to that middle column. Of those 10 documents, we see that 6 of them are actually responsive according to the person. That is always correct. The person says they're responsive. 6 out of 10 of them are actually responsive. So 60% is our precision score. That's what precision means. For recall, remember, recall is what percentage of the actually responsive documents did the algorithm predict? Okay, so the algorithm predicted the ones in the left-hand side of that circle, so that's the same numerator as we used for precision. But now the denominator is all actually responsive documents, which is the left-hand side of the diagram. And again, we have these kind of things at the top. You will get slides. You will have access to the slides for this presentation, so you can pore over that. So from a table point of view, recall, we start with the truly responsive documents, which is in this right-hand column. And of those truly responsives, how many are actually, or how many are predicted responsive? So 3 out of the 4 are predicted responsive. 1 is predicted not responsive. That means that our recall rate is 75%. Okay. Now there's this other thing called F-score or F-measure or F1, or pretty much if I see a word beginning with an F, I just assume they're asking about F-measure or the F1. So what is the F1? What it is a number that allows you to blend precision or recall into a single calculation. I would say this is not that useful in our world in e-discovery, and it's for those reasons I talked about when I was talking about the medical tests. The two errors are not to be treated equal, but if you're comparing 50 different algorithms, this is a way to compare them so that you can't game the system and get perfect recall and terrible precision, or vice versa. What it really is it's called a harmonic mean. It's an average, but it's not like an arithmetic mean like you and I are used to, and it penalizes you if one of your scores is particularly bad. But like I said, I don't think that this is great, but I figured I'd talk about it. So as an example, if you have 60% precision and 75% recall, the normal average that you and I would think about is like 67.5, or it is 67.5. The arithmetic mean, or sorry, the harmonic mean of those, the F measure, would be 66.7%. So that's what F-score is. I won't spend too much more time on it. Let's talk about elusion. So elusion asks, did we just throw the baby out with the bathwater? Okay, what do I mean by that? Elusion rate measures of the documents that you're throwing away that are predicted not responsive. How many of those are good? How many of those should we be keeping? Okay. So what I like about elusion is it really cuts to the core of what we're trying to do. The whole point of TAR is to avoid or at least delay reviewing junk. And this measures what is the penalty the cost of that? What is the how many errors are we introducing by that? So the way we calculate elusion is we look at the predicted not responsives, and we say which portion of these are in fact responsive. Okay, so again, back to our diagram, predicted not responsive means outside the circle. So we say what percentage of the ones outside the circle are in fact responsive, which is this left-hand side of this thing. I don't even know what kind of shape that is, divided by everything outside the circle. So in our case, our elusion's pretty poor. It's like, almost half. But generally speaking, your elusion rate will be in the single digits if you're doing a good job. I will say that very much depends on the richness of the collection, so how many responsive documents are out there. If there's very few responsives, it's easy to get a good elusion rate. If there's very many, it's harder. So elusion, like recall, you have to kind of consider your responsive rate when you're trying to interpret how good you did. So here's what it looks like in a diagram again. There's my predicted not responsives. That's my universe that I calculate from. I have one responsive, so elusion is 1 out of 4. Elusion, you always want low numbers. Precision and recall, you want high numbers. So that's another difference between elusion and those others. So if you're not familiar with elusion, why do we need another number? What's wrong with precision and recall? So I think elusion does some good things for us. First of all, it's very directly, it's easy to understand. It's directly measuring the action or the penalty associated with that action. We're proposing to exclude these documents. You say, well, what's the downside? And I say, well, the downside is this error rate. I'll also say, I alluded to this before, but recall can be very expensive, especially with low richness, and in order to get a decent recall number, you might have to review thousands and thousands of documents, which is tough, especially because you're typically wanting to set these documents aside before you begin. I'll talk about that a bit in the demo. So recall can be very expensive. Elusion's better there. It does avoid having to deal with control sets, and there's a lot of problems associated with control sets. I won't go into all of them, but there's a lot of people that vociferously dislike control sets, and with elusion, you take your sample at the end, not at the beginning, so it avoids some of that. And also, if you need to get recall and you've coded all your high-ranking documents or all your predicted responsive documents, usually high-ranking in an algorithm, then it's easy to calculate recall from the elusion. If you haven't coded all your high-ranking documents, it's a little bit trickier, but this is another advantage of elusion. Let's talk a little bit about margin of error and confidence as it relates to these statistics. So you absolutely, when you do these statistics, you typically do them on a sample, and therefore you should communicate your margin of error and confidence level for the measurements. To calculate those, you need to know your sample size and you need to know your population size. But in this case, it's not just everything. The population is the pool from which it was drawn. So in the case of precision, that pool is all predicted responsives. In the case of elusion, that pool is all predicted non-responsives. It's easy to get that, to define that population, because the algorithm predicts everything. So I have, if I'm using active learning, for instance, I can look at all the documents, I can update my ranks, look at all the documents that are predicted to be non-responsive, below my cutoff score. I know exactly how many documents there are, and that's my population size. Then I draw a random sample, that's my sample size, and I'm done. The tricky thing is with recall, because with recall, the population is all actually responsive documents. And as I said before, if I knew what the actually responsive documents were, we wouldn't be here, right? That's what we're trying to determine. So what you end up having to do with recall to get a margin of error is you got to take a large sample. You have to code the documents in that sample, and as you find responsive documents, that becomes your sample size. And the population size, that's really just got to be an estimate based on richness. So recall is much trickier to calculate these numbers on because of those factors. Again, that's another reason that elusion can be better. Okay, so let's look in relativity again, and I'll try to show you a bit more of what I'm talking about. So I've got a different dashboard here that shows my precision and recall. Okay, I think it's painting. Okay, so in this dashboard, I've got my TAR prediction in a widget here. I've got some reviewer designation represented here as well. Let me clear my sample from before. That's one of the things about doing these samples is you need to make sure to clear them when you see that orange. Okay, so here you see my 64,000 documents. I've got all of them predicted to be responsive or not responsive, and I've only got some of them coded. Now, when you're really doing precision and recall, it is important to use a set that's been pulled out ahead of time that the algorithm doesn't know about. And that's simply because these algorithms, if you tell them that document X is responsive, it's more likely to classify that document as responsive, right? If you tell it the answers to the test, it'll do better on the test. So you need to pull documents out to measure this properly, and that's typically done ahead of time in a control set. For the purposes of this demonstration, I haven't pulled documents out. So if I wanted to measure precision, what I would do is I would take the predicted responsives, which in this case is 6,000 documents. I would sample them, and I would see how many of them are coded as actually responsive. So I could sample these. Maybe I do a sample of 50 of them, and then I would go through and check how many of the 50 are predicted responsive. Now, as you can see, 11 of them are predicted responsive, 39 have yet to be coded, so I'd go code those. But again, the way I'm doing it right here is not quite right because I'd want to do this ahead of time so that the algorithm doesn't know about these documents. So I'd want to start pull them out ahead, draw the sample out ahead of time, set it aside, and then, or I could draw my sample from documents that have been set aside. For elusion, again, I would start with let me clear my conditions out here. I would start with my predicted non-responsives and draw a sample of those. Now, elusion you can run at the end. The idea of elusion is we would exclude the ones that are already coded, and we would just be looking at the predicted not responsives that have not been coded yet. We would draw a sample of those, say 1535 or whatever, sample them, and then we could go code those documents. And once we've coded them, we know how many documents are actually responsive, and that gives us our elusion rate. To do clear out my conditions again, clear out my samples, clear all conditions, clear sample, yes, clear. To do recall, what we need to do is sample everything, code that sample, and then what we're left with that's coded responsive, those are the ones that we would use for our recall calculation. So again, notwithstanding the fact that I would want to pull them out of my model, I could sample, say, if I sampled like 2,000 and I've got 10% richness, that means that I would expect only what did I say, 10%? Only 200 of those documents are actually responsive. So that would be like the denominator of my recall calculation. That would be the sample of my recall calculation. So you always have to draw from a bigger sample for a particular margin of error to get recall. So recall tends to have larger margins of error for a given cost. Okay, so I'm not going to get too much deeper into that today, but hopefully I gave you a flavor of how you might do these things inside relativity. Okay, so that really brings us to the wrap up. So I hope over the course of this session you learned some things. I hope you learned that certainly sampling can be a very powerful tool. Statistical sampling, random sampling can be a very powerful tool that can save you time, can save you money. It's super easy to do in relativity. It's easy to do other calculations using some of these calculators on the internet. But you should really use it when the conditions are right. So when are the conditions right? It's when you need to know how many of something are out there. You don't need to find all instances, at least not yet. You just want to find how many are out there. So estimating frequency. And if you have those conditions, by all means, consider it. It's good practice to report your margins of error. Don't be like the people in the newspaper that say candidate A is winning and doesn't tell you how. Precision, recall, elusion, we talked about those. You should report your margin of error and confidence there as well. You need to pay attention to that denominator. And if you do that, then you can get some sense of how your algorithms are doing and how things are going. So with that, I'm going to open it up to questions. I saw a couple came in. Sorry I didn't get to them ahead of time. Actually, one question I would pose for the audience is, so I mentioned a few places where I like to use statistical sampling and relativity, random sampling and relativity. Are there other places that you like to use random sampling that I didn't mention? So I mentioned like measuring OCR errors, measuring processing errors, production images, coding decisions. Are there other things that you guys have that you might be able to suggest that I could share with the audience? If so, please type them in. So some of the questions that came in, yeah, so when I showed the slide about the sample size, let me bring that slide back up. It's this one. So basically what this is a curve that's growing very, very slowly. So the sample size of 384, 384, 384, it's like a very logarithmic function it's not completely flat. You could probably get to a number where it would tick up to 385, but it might be like 100 gazillion. So it just flattens out. If you looked at this over time, it just flattens out very rapidly. So 1535 I think is where the plus or minus 2.5% tends to flatten. 384 is where the plus or minus 5% tends to flatten. So these numbers kind of get burned into your mind as you do more and more of these. You could always use 384 out of 500. You could use a larger sample on the lower ones. That'll tighten your margin of error. But of course, there's always cost associated with those sample sizes. But if you plug them into the calculator, you get a sense of it. And yes, it's kind of magic. It's the magic of math, I guess. There's a question about resources for using widgets. So yeah, there's definitely loads of documentation about using widgets on the website. There are some other webinars, I think, about visualizations, using visualizations in relativity. But when I'm doing a demo, if I can figure out a way to use the widgets, I think it really kind of pops, and it really it's easier to demo because you just have to click, you don't have to type, and then you don't misspell something. But yeah, it's absolutely something that's a good practice to use when you're using relativity to drop those widgets in. But I can follow up maybe with some resources if a quick webinar search doesn't seem to reveal them to me. Yeah, the way I use them for sampling. Okay, let me follow up with you on the question about the widgets. Don't have any other questions coming in. So, what I would say is feel free to reach out to solutions, solutions@relativity.com if you have questions about using these types of approaches. We are a team of folks that loves consulting on workflows and loves brainstorming with you on ways to use the product better. Do share with us ideas for future webinars and that kind of thing. There's also a survey that you can fill out to tell us how this one went. So please do that as well. I love doing these things. I thank you for your time and your interest, and the recording will be up on the website if you want to tell others to come watch it as well. So ended a little early, but thanks so much. Have a great rest of your afternoon, and thank you for giving me some time out of your day. Take care.